Hello and welcome everyone. Good afternoon, good evening, good morning, depending on where you're joining us from. My name is Chris Rogers. I'm CEO of Sensimal. And along with me, I've got our CTO, Chris Narowski, for this week's session of the QuickLogic, QuickFeather, and Sensimal Analytics Toolkit tutorial series. I welcome you to this session. If you're joining us for the first time, welcome. If you're here from last week's session, welcome back. Today's discussion will be focused specifically on the use of TensorFlow Lite, the Google TensorFlow Lite neural network platform, and how to integrate TensorFlow Lite models with the Sensimal pipeline to get the best of both worlds between the two tools. And we'll describe what some of those benefits are of combining the capability of both software suites. So without further ado, I'll turn it over to Chris Narowski and we'll get started.
Okay. Hi, everyone. Thanks for joining. My name is Chris Narowski, and like Chris Rogers said, I'm the CTO at Sensimal. And today I'm going to be going through a tutorial, a full end-to-end tutorial for building a condition monitoring application for a fan. And we're going to be using TensorFlow Lite along with the Sensimal pipeline for feature extraction. So to start off with, I want to give a little bit of background on Sensimal. So at Sensimal, we sell a TinyML toolkit for smart sensors to application developers and system integrators to enable them to build, rapidly build novel applications for edge devices. And the way we do that is with a suite of tools that help users capture and annotate their sensor data, to explore their data and build machine learning models to help classify that data. And then finally, we have an embedded SDK for that we can compile those models into that is optimized for running on resource-constrained embedded devices. And we have a suite of tools to help users, once they've flashed those binaries to their device, validate the test data so that they complete their end-to-end machine learning workflow. And so I want to before we get into the technical details of actually building the pipeline, I wanted to give you a broader overview of the Sensimal architecture so that you can understand how to build your project and how all of the pieces fit together. So typically when you're starting a machine learning project, the first thing you're going to do is you've come up with an idea. And in our case, we typically focus on classifying time series sensor data. So you want to be able to figure out what is going on at your device that's in the real world based on some sensor data that it's collecting. And so you come up with your idea and you design a data collection methodology. And once you have the data collection methodology, you need to get the sensor data off the device and label it. And so that's kind of the first part here, where you start with our Sensimal Data Capture Lab, where you can stream sensor data in or upload CSVs and ingest those into our toolkit. And you can use the Data Capture Lab to collect and label that data, to perform automatic segmentation, or to manually label your events of interest. And the Data Capture Lab communicates with the Sensimal Analytics Cloud. So you can sync your projects across your team. So if you have multiple people working on your team, you can share data between them, share the labeling tasks, share your models. The next piece of the puzzle is our Analytics Studio, which is a graphical web UI that enables you to build queries, use AutoML to create machine learning models, test and validate those models against the raw time series data that you've collected, and understand where the model is performing poorly, which capture files, where in those capture files it's performing incorrectly, and identify the different classes that you need to work on. And then finally, you can download knowledge packs in the Analytics Studio, which can be downloaded to your target platform. And you can do that in terms of if you want to download the library code so that you can build your application around the knowledge pack, or you can download the binary, which is a full complete application that's used as part of the POC phase to get you up and running fast. And then you can also download the source code depending on which tier you've subscribed to in the Sensimal Cloud. And another piece of the puzzle is the Python client. So a lot of times the first thing we do is we go in and we use AutoML to build our models. And once we have a good model, we want to tune that model, maybe tweak it a little bit to up our performance. And so we use our Python client to be able to do that. And the Python client provides programmatic access to building a pipeline. So you can choose each individual step in the pipeline, tweak the tuning algorithms for the training algorithm, and you can even combine multiple models to build an ensemble or a hierarchical model to improve the performance. And then finally, once you've got a model that you're happy with, you can download the knowledge pack, and the knowledge pack is the firmware that lives in your app, where it's running on your device and you're sending sensor data in and it's returning a classification to you. So I want to dig a little bit deeper into what I mean by the Sensimal pipeline. And so for time series classification, the way a Sensimal pipeline works is you have raw sensor data coming in. It can be any number of sensors that are time series sensor data. And it's fed into the knowledge pack, which has segmentation, where it defines how we're going to segment the data before sending it down the pipeline. You can also add different filters, different sensor transforms into this part of the pipeline. The next part of the pipeline is the feature extraction step, where we have a library of over 80 different feature extractors composed of a variety of different types, such as MFCC or frequency statistical type features. Once you've extracted features from your time series sensor data, the next thing we do is feed that to the classification algorithm. And so the Sensimal Toolkit has a number of different classification algorithms built in, such as nearest neighbors, RBF kernel, boosted trees, decision trees, bonsai trees. And we also support the TensorFlow Lite micro inference engine. And so that's actually going to be the classifier that we're going to focus on in this talk, is building a pipeline using all of these different tools within the Sensimal Toolkit, and then finally training a neural network model to use the feature output to recognize what's going on in this model. And once you've generated your firmware, we're going to flash it to the Quick Feather. So the Quick Feather has a number of different parts, and the knowledge pack, which is composed of the segmentation, feature extraction, classification, is going to be running on the M4 processor. So today for this demo, I thought the best thing to do would be to walk through an end-to-end example to give you an idea of what building a machine learning project is like and kind of the different steps that you're going to go through. Now we're going to use a simple example, which is a fan state condition monitoring application. So we can kind of think of, if we put our predictive maintenance hats on, we can think of a scenario where we have hundreds of fans installed in our factory. And right now, the only way we know if a fan is failing is when the equipment that they're cooling starts to heat up. So what we want to do is get ahead of that and put some sensors on our fans to detect when the fans start to fail, so that we can do predictive maintenance and get ahead of any of these issues. And the only challenge is that the fans are in hard to reach locations, so we aren't able to walk around and look at them visually ourselves. So what we're going to do is we're going to build an algorithm that can identify if the fan is off, if it's on, if the mount is vibrating, or if the flow is blocked. So those are the 4 classes that we're going to try and identify. And the way we're going to do that is we're going to use just the IMU sensor. So it's an accelerometer sensor, and it has it's going to look at accelerometer X, Y, and Z directions. So the acceleration in those 3 directions. And that's the only sensor that we're going to use for this application. And I'm going to mount, so here's the quick feather board. And we're mounting the quick feather board into the ESP32 Wi-Fi module so that we can stream our sensor data out wirelessly over Wi-Fi, and also stream our classifications out over Wi-Fi. And so the different steps I'm going to walk through is, first, we're going to use the data capture lab to capture some sensor data and then annotate it. I've already collected a number of files for this project, so I'm going to walk you through what I've already done and then show you. We're going to go ahead and capture some more. After that, what we're going to do is build a query to train that model, to pull the sensor data out, train the model using TensorFlow Lite or TensorFlow, convert that model to a TensorFlow Lite model and upload it as part of our pipeline. And then finally, I'm going to deploy the model to the device. So I'm going to download the knowledge pack, flash it to the device, and we'll look at the results in real time. Okay. All right, so let me start by going to the data capture lab so we can see. Okay, so I'm going to open up the Sensimal Data Capture Lab, which is a Windows application for collecting and annotating data. And I have a number of projects. I'm already signed into my account. So I'm going to go ahead and open up the Quick Feather fan demo project. I'll just orient you in the Data Capture Lab. So when you open it up, it's a blank screen. On the left here, I have my Project Explorer. And so when I click on Project Explorer, I can see information about all of the captures that I've already collected. And so you can see in the left column, there's a status icon, which lets me know, is this file local, or is it in the cloud, or is it both? So in this case, this file right here is only in the cloud, and this file is both in the cloud and on my local machine. And so if I wanted to download any of these, I can just double click on it, and the Data Capture Lab will just automatically download that file and display it in the view. And so what we're looking at here, and so what we're looking at here on this top graph, I'm displaying the accelerometer X, Y, and Z data on a single graph. And then down here, I'm displaying accelerometer X only, accelerometer Y only, and accelerometer Z only, just so we can get a better feel for it. And on the right here, we actually have our video that's synchronized up with the time series sensor data. So as we move the marker here, we can see exactly what's happening in the video. And that's going to help us label our sensor data better. One of the challenges that we often find when we're working with time series sensor data is that you need a very good data collection methodology, because unlike image data, where you can look at it after the fact and label your data and know exactly what it is, or if you have audio data where you can listen to it and know what's going on, when you're working with time series sensor data, it can be really difficult, if not impossible, for you to interpret without having either some video synced up with that data set, or just a really great data collection methodology where you know exactly what's happening in that time period. So when I opened up this project, there was no, it was a blank slate. And the first thing I did was I went to project properties and I created the different segment labels. So the segment labels identify are the events that we're interested in. So for this project, I said I was interested in detecting 4 classes. So flow blocked, mount vibration, on and off are the classes I created. And then I also created some metadata. And so metadata helps me to capture the context of how this data set was, how that file was collected. And it's really useful later for going back and filtering out or building a query that only pulls out specific types of data. So I'm just going to go ahead and add one more here. I'm going to say it's surface, or we'll say collection surface. And then you have the option to make this a text input field or a drop-down field. I'm going to make it a drop-down field, and I'm just going to add desk as the only field here. So now I've added another metadata segment to my list. And so when I come and I look at my Project Explorer now, I see that collection surface is here, and it's completely unlabeled. So if I just right-click here and hit Edit Metadata, all of these were collected on my desk, so I can hit done. It'll save that metadata. And so now all of these files are associated with metadata. So if I was building a model for a fan that was collected in different types of locations, I could add that to the metadata and try and build a model for all of them together. Or if I might find out that it's best if I build a model for a particular type of surface. Okay, so before I show you how to label data, let's go ahead and capture some new data. So I'm going to switch to capture mode in the data capture lab. And I've already created my sensor configuration. And sensor configurations help us keep track of how data was collected. So when we're running our models, we always want to make sure the type of sensor data that they're trained on is the type of sensor data that they're run against. And by creating capture configurations, it helps us keep track of how the data was collected. So in this case, I know the device, method of collection, I know the sample rate, and I know which sensors, along with what the settings for those sensors are. And so I'm going to use live stream capture with Wi-Fi. So over Wi-Fi, so I'm connecting to the ESP32 to collect the data. Here's the address. So I've already gone through the setup. If you are interested in using the Wi-Fi module, we have documentation on sensimal.com/documentation for adding that board to the Quick Feather. Otherwise, you can hook up directly over the serial port and stream the data that way as well. So before I collect data, I'm just going to collect data for on. I'm going to specify the collection surface, and then the data set, I'm going to collect this as test. So one of the things I do when I'm building a machine learning project, and a lot of standard best practices, is to have a training set and a test set. So when you're training your model, you can train and validate and do cross-fold validation against your training set, but it's good to have a portion of that data held out for a test set, so you know, is my model going to generalize and work well on data it hasn't been trained on? So one of the things I do when I'm building my data collection set is to set aside some data for test. And I do that by through the metadata here. So I'm going to click connect. And so now it's connected to the sensor. I'll move my webcam over here. So here's the device right here. And I'm just going to turn the fan on by plugging it in. And so now you can see the shape of the sensor data has changed. And so in order to record this data, I'm going to come out to my settings, actually, and specify a timer. So I'm just going to record 15 seconds of data and click save, and then set begin recording. And so what the timer is going to do is it's going to start collecting data, and as soon as it reaches 15 seconds, it's going to stop. So this is a nice way to kind of keep track of how long you need to record for as part of your project. So once the limit's reached, the data is saved locally and also synced up to the cloud. So now when I come and look at my Project Explorer, I can see that there's a new file here that I just created, and it's been named on, and then the timestamp for when we collected it. And if I open it up, so here's the full sensor data that we just recorded. And to label it, I can just right-click here and drag on the graph, hit this edit button here, and I would label this as on. And so all of the sensor data here that we just collected now has the event label on. And so later when I go to build my model, I can pull all of that data into my model and just hit save changes. And I'm going to switch over to this file right here, and we'll just label the individual parts here. So when I look at the fan video here, I know that I can see that here's a transition point. So right here, the fan was off. So I can click edit off. And this point right here, the fan is on. So what I'm going to do is label this section as on. Delete this one. This section right here, I can look and see that the flow is blocked. So I'm going to put a marker down here and say flow is blocked. And then this last section right here is where I'm shaking the base. And so we call that mount vibration. And I can say mount vibration and click save. And so now I've labeled this entire file so that when I go to test my model against it, I'll be able, it'll be able to report back how the accuracy for this particular model. So now we've gone ahead and built a corpus of data, labeled data that we can use to train our model against. So now what I'm going to do is switch over to the Analytics Studio, where we're going to start building our query. And then after we've built our query to create the data, I'm going to go to a Google Colab notebook where we can actually build the individual steps of the pipeline using the Python client and then train the neural network model. So the first thing I'm going to do is I've already logged into my account, and I'm going to open up the Quick Feather fan demo project. So when I open up the project, the first thing I see is an overview, which tells me some information about this project. So I can see I have 32 captured files. I've built some models and pipelines already. And I can see some information about which sensors are being used in the project. What are the different classes that I've labeled? And then what metadata I have. And you can also add some additional information down here using Markdown to kind of give you a project description and help you remember exactly what this project is for. So the first thing I'm going to do is in here is the first step is to always build your query. I've created one query, but we're just going to create a new one to get started. So I'm going to click Add New Query and type a name for the query. So I'm just going to call it fan demo query. The session is manual. So whenever you create a DCL project, the first thing you need to do is create a session. And that's a way of versioning the labels you put down. So in this case, I named my session manual, and you can have multiple sessions. So if you had different people labeling, or you wanted to version the segments that you have at this point before making some modifications, you can do that using sessions. The label name is label. And then I'm going to go ahead and add the data set and the capture UUID as my metadata. And so this is going to allow me to group the data I have by the metadata. And I'm going to build a query filter against data set. So I only want to pull in my training data when I'm building my model, and hit done. And then I can hit save here. And this will create the query and return some statistics about that query data. So right here, on the right here, I can see information about the data I've collected. So it's telling me I have 7 segments for fan blocked, 11 segments for mount vibration, 3 segments for off, and 9 segments for on. And then I can also switch the view and look at samples. So segments just means in the data capture lab, I put a start and end marker down. And then samples tells me how much actual data there is that has been labeled for these different classes. And so I have close to an even amount of data, a little bit less off data than the other data sets, which is fine. So if I were to want to use the AutoML to build this model, I would come into build model screen and I can specify the window size. So if we wanted to have, for this project, we're going to use a sliding window. So this would tell me how many samples of data I collect before a classification occurs. So in this case, it would be 4 seconds of data since we have 100 Hertz data. And then you have a number of other advanced settings that you can use to tune this algorithm. When it searches the parameter space before you click optimize. And when you hit optimize, it's going to go and run through a number of different, it's going to search the parameter space and run a couple hundred different models and return the top performing models for your data set that it finds. But for this tutorial, we want to train our own neural network models. So I'm going to walk through how to do that now. So I'm going to go over to Google Colab. So if you aren't familiar with Google Colab, it's a free Jupyter Notebook environment. So if you want to install Jupyter Notebook locally on your machine, you can do the same thing. You just also have to install TensorFlow as well as the Sensimal client. But if you use Colab, it's already installed and it's free to use. So it's really easy to get up and running there. The only thing we need to do is when we open the Colab notebook is we need to install the Sensimal client. So you can do that by running this command here. And that's just going to install our Python client to the Colab notebook environment. And then the next thing you need to do is to log in. So right here, what I'm going to do is import the Sensimal client. And then when I type this command here, DSK, which stands for Data Science Kit, equals Sensimal, it's going to ask for your username and password, and it will log you in so that now you have access to call the different REST APIs. So the next thing I'm going to do is I'm going to connect this client to the project that we want. And so dsk.project, and then I pass the name in, so Quick Feather Fan Demo. And so what it's doing now is it's optimizing it for querying. So it's building the backend index for this project. And then the next thing I'm going to do is create a pipeline. And so pipelines you can think of as sandbox environments where you would build your models and train your models, and it'll help you keep track of the history. And so what we do is we build a pipeline locally with the client, and then we tell the Sensimal cloud to execute that pipeline and return the results. So I'm going to connect to this pipeline. TensorFlow Lite Micro is what I call it. And then the next thing we're going to do is we're going to start adding steps to our pipeline. And so we have a lot of documentation for how to do that. So if you click on this link, and so I'll share this notebook as part of the tutorial afterwards. If you click on this link, it'll take you to the pipeline functions, which gives an overview of all the functions that are part of the Sensimal toolkit. And so when you're building models with the Sensimal pipeline, we've already created a number of functions that also have optimized C code. And so you're building a pipeline using the functions we've already created. And there's a number of different types that you can think of. So sensor transforms is, as data is coming in, we can apply a transform to it, such as taking the magnitude or adding a low pass or high pass filter, which would be sensor filters. There's segmentation, which is where we decide how much data should be fed to the rest of the pipeline. Segment transforms are applied to those segments, such as demeaning that segment. The next is we have feature generators, which generate, take the segments of data, extract features from them. And then we have feature transforms, which are going to operate on the features we've extracted, and finally classification. So in this pipeline, I'm going to go through all of those steps. So if you want to see a list of all of the features that we have, you can go to the documentation. You can also say list functions, and it'll tell you the name, the type, the subtype, and then a short description of that function. Okay, so let's start by building our pipeline. So the first thing I'm going to do is I'm going to say list queries, and that's going to list all the queries that we've created for this project. And so we have 2 queries. I'm just going to keep the one that's already here. And so the first thing I'm going to do is I'm going to say dsk.pipeline.reset, and that's going to set my pipeline state to blank. And then I'm going to say set input query demo query. So that's going to add a single step to the pipeline. And the first step in your pipeline always needs to be an input query or an input file. So you can also upload raw CSV data and build against that. So you might be wondering, how do I know what I can add? So if I type this right here, so we have a function called snippets. So if I type dsk dot, and when I hit the dot, it does autocomplete. And I can say snippets dot, and this is going to give me a list of all the possible different types of things that we have. So for example, I wanted to do a feature generator. I could hit dot and it'll list all the different feature generators that you can use. For this case, the first thing I want to do in my pipeline is add segmentation, and I want to use a sliding window. So if I print dsk snippets windowing, segmenter windowing, I can see this would be the call I would use to add the windowing segmenter to the pipeline. If I want to see a description of that, I can go to the docs, or I can also type dsk.function description, and it'll print out information about this function, information about the parameters, and give you an example of what running it would look like. So I'm going to go ahead and add this to the pipeline. So I'm going to give a window size of 400, a delta of 400, which means there's essentially no overlap. So we're going to wait for 400 samples, compute a class of features, and have a classification. Then wait for another 400 samples, extract the features, and give us a classification. If I wanted to do a classification every second, but still have a window use 400 samples, I could set delta to 100. And so basically every new 100 samples, it would use the previous 300 plus the new 100 to compute your classification. And so I've added windowing. So now you can see there's 2 steps in the pipeline. So the next thing I want to do is I'm going to add a transform, which is to demean the data. And so we're going to pass the input columns, our accelerometer X, Y, and Z. So I want to demean all of these columns. And the type is mean. And so to add that, I just add this now. Oops. I executed it out of order. Add windowing. So now we have the 3 steps in the pipeline. And the next thing we want to do is add a feature generator. So if one of the things you can always do in Python is if you type the name of the function and then put a question mark, it will bring up the documentation over here on the right. And so you can come and look at the documentation to get a little bit more in-depth understanding of the different ways you can add features. But in this case, what I'm going to do is I'm going to add, I call 2 subtype calls. So one is rate of change and one is statistical. And what that'll do is just add all of the statistical features and add all of the rate of change features. And then I'm going to add one feature by specifying its parameters. So in this case, the name is MFCC, and I'm passing in the sensor column. So I want to compute it against all of these sensor data, and then I can pass the parameters, so sample rate and Sepster count. So we only are going to compute the first 10 MFCC features. So I can go ahead and run this cell, and then I'm going to just run execute. So I say feature vector. So this is one result, and this is S, comma S. So it returns the results, and then it returns statistics about summary information about the execution run. And when I run dsk.pipeline.execute, it actually executes it on the server and returns the results. So I'd previously run this, so it ran from the cache, so the results return really quickly. And then if I look at what's returned, so that it's returned as a data frame. And I can see on the left here all of the different features that were extracted. And then across the top, these are the different feature vectors. So the data set, so here's the metadata data set that we had. So training, the label for this feature vector is flow blocked. Segment ID is 0. This is the capture UUID, so I can tell which capture it was computed from, and the segment ID tells me where in the capture it was computed from. And then you can see all of the features for that particular segment of data. Now, since we're running on embedded devices, we don't necessarily want to have to compute all of these features because we have resource constraints and latency issues that we need to think about. So one of the things we can do is we can pare down the total number of features that we need to extract by using a feature selection algorithm. So I'm going to use a feature selection algorithm. I'm actually going to use 3. So the first 2 are variance and correlation threshold. So those are going to remove some features, and the final is a t-test feature selector. And then the next thing I'm going to do is I'm going to scale the resulting output. So as you can see here, these right here computed as the outputs are all float. We actually want to convert those down to a single byte before feeding it to the classifier, because that's going to save us a ton of space on our classification. So I'm going to run these 2 cells right here. And so you can see, again, a summary output of all of the generators that are being run, along with the selector set and the scaling algorithm that we're running now. And now I'll execute the pipeline. So the results are returned. So we'll just look at it the same way. So now you can see so instead of having a couple hundreds of features, now we only have 12 features that we're computing for our pipeline. And we can use this cell right here to visualize it. So I can see all of the different features in my pipeline. And now we're ready to train our TensorFlow model. So what I can do here is, if you run this cell, it's going to take the Sensimal features and convert it to a train and test set that's ready to be fed into TensorFlow. And then now we're ready to build our TensorFlow model. So we're going to take the features that we just computed, feed those into a TensorFlow model, and then train that model. So if you're familiar with TensorFlow and Keras, we're just setting up a simple neural network that has 3 layers. And so I'm going to run this cell right here, and it's going to create the neural network architecture. And then run this cell here, and it's going to train the model on those features that we have. And so again, all of this will be in the Colab notebook that we share. So you'll be able to walk through these steps and understand it yourself in more detail. And so what this prints out here is the training loss and validation for both the validation data set and the training data set. And on the bottom here, it's the accuracy for the training data set and the validation data set. And then over here is the confusion matrix. And so the accuracy for this model is really high, both in the train and the validation set. So now we have our model. The next thing we want to do is quantize the TensorFlow model and then upload it to our server. So you can run these two cells here, and what it'll do is it'll quantize the TensorFlow model, which in most cases it converts any floating point operations to int8 operations, which gives you a much smaller model size, as well as it can be much faster to execute on a microcontroller when there's DSP acceleration built into that. So one thing I'll mention here is when you're building your neural network model, so we're using TensorFlow Lite Micro as the inference engine. And TensorFlow Lite Micro supports a subset of the overall TensorFlow ops. And you can see a list of the ops that are available in TensorFlow Lite Micro. If you go to the TensorFlow Lite Micro documentation, or if you click on this link here. Okay. And so now for the final step, we're going to take that model that we've just created and upload it back to the server. So I'm going to say dsk.pipeline set training algorithm and load model TF micro, and I'm just going to pass that model in. And then I can say results.summarize. So it's going to take that model, load it into the cloud, and now it's going to run it through our entire data set and give us the results back. And then so you can see the accuracy for this model is really high, and the confusion matrix for this model looks really good. The final thing you need to do in order to run your model is to call model.knowledgepack.save. And what that's going to do is it's going to save the model that you've created and persist it to the server with that name. And once you've done that, you can come back to your project in the cloud, and we'll run the final validation here. So if I click on Quick Feather Fan Demo, and I'm going to go to my knowledge packs, so I can see a list of all the knowledge packs that I've created. So here it tells me the classifier, the accuracy, the model size, the number of features, and more information about the model. So here's some models that we ran with the AutoML for this process, and you can see they also get really good accuracy. And they're simpler classifiers, so they take up less size on the device. So I'm just going to click on the test model. So when we go to test model, you can test your data set against the data you've collected. So what I want to do is click on filter here and click test. And then we'll just select all and say compute accuracy. And this is going to actually compile and run your model in emulation and return results that tell you how that model is performing against that collected data set. And so you'll be able to look at each individual file and see what classification it gave for which portion of the file and how that compares to what you labeled it here. Okay. Okay, so here's what the model comes back with. And so you can see that there's a little bit of poor performance in this part, which is okay. Typically, when you're building a project, that just tells us that we need to collect some more data for mount vibration. So typically, when you're building a project, you start off by collecting an initial data set, and then you train your model, and you get a feel for, where is it performing well, where is it not performing well, and where it's not performing well, you can go back and collect some more data to help your model perform better in that case. So if I click on one of these files, I can see the results for that file, and you can see a confusion matrix that tells you which classes were predicted versus what those classes should have been, so you can understand where your model is getting confused. So the next step is to go ahead and download the model. So we're working with the Quick Feather. So we're going to select Quick Feather 1.70. The format we want is binary, so we can download it that way and flash it directly to the device. And then we only want output simple streaming. So you can just go ahead and click download at this point. What it's going to do is compile the entire pipeline. It's going to compile an optimized version of TensorFlow Lite Micro for your particular model, which only has the ops that you need specifically for that model, and link it all together so that all you need to do is flash it. And it takes out a lot of the need to set up that pipeline flow. So I've already flashed, or I've already downloaded this model. So what I'm going to do is go ahead and flash it. So to do that, I just connect the Quick Feather board to USB, and I need to click the reset button or the power button, and then the user program button. And I'm going to use the tiny FPGA programmer to download the file and flash it to the device. Okay, all right, so now the device is flashed. So I can just go ahead and power cycle it. And I'm going to hook it up with the battery power. Just so we can get a fully autonomous endpoint. So when you flash it, you'll see the LED blink 3 times or 5 times and then turn off. And so to connect to it, what I'm going to use is the streaming gateway. And so I just need to configure the gateway. So it's going to use the TCP IP connection. We're going to set recognition mode, and I just say configure. So it configures the device. And then I can come over and I can say connect, which will start it streaming. So right now it's sending out, it tells me the model ID and the classification results. If I want to know what they correspond to, I can look here in the class map. So 1 corresponds to flow blocked, 2 mount vibration, 3 off, and 4 on. So right now it's telling me that the fan is off. So if I plug the fan in, so we should see, so mount vibration while I was turning it around. So now 4 is fan on. And then I can go ahead and block the flow. We'd expect the model to switch to class 1, which is flow blocked. And then finally, I can vibrate the mount. And we'd expect it to switch to class 2, I think. We got disconnected. Oh. Yeah, there we go. So now we're seeing class 2 come up. So that gives us a feel for how you can validate these models. We can also look at the streaming data over the UART and see the classification output there as well. So now it's just back to on classification. So that concludes the entire walkthrough tutorial where we were able to capture and annotate data, train a model using by extracting features using a Sensimal pipeline and building a neural network. And then finally, we deployed it to the device and validated that it was working how we expected it to work. So thanks for attending the talk. Again, my name is Chris Narowski. I'm the CTO at Sensimal. You can reach me here. You can go to sensimal.com and contact us as well as through our site or post on the Hackster.io. If you have questions there, we're happy to answer them.
And we also have a series of questions here that we're going to cover before we sign off.
Yeah, and so we'll do some Q&A before we go out.
Okay, starting with, so one question that was asked was whether the ESP shield is being used. We use the Huzzah 32 feather board. And Justin has put a link there to where that can be identified, as well as the documentation. Another question on which module, again, same link.
Yeah, so if you go to our GitHub, Sensimal, or in search Sensimal GitHub, you'll see our repos. And so the ESP32 simple HTTP UART is the application, and it has documentation for how to connect it to the quick feather board.
Another question was, where is all the documentation for this project? We have two sources. One is obviously this presentation will be posted, so you can go back and reference this at any point. That'll be up within the day. We also have a documented version of a different demo using boxing glove and punch recognition. There we go. So that's under documentation. If you go to support documentation, then you'll find it there under application examples.
Yep, so this one walks through again, doing the same thing, but for a different application, but still using TensorFlow. And then we also have the application example for the same fan demo, but using AutoML to build the model.
Next question was, is there a document for interfacing Sensimal with Jupyter Notebook or Jupyter Lab? There's a link here Justin's provided on a Python project or Sensimal.
Chris, sorry, I think you might be on the answered tab.
Yes, yeah, I'm just covering some of these and we can go to some of the open ones.
Okay.
Yeah, so I think in here we have a notebook already posted, so you can come here and try the notebook yourself for this one. And I'll also be posting the one I just did later today.
And now switching over to the ones marked for live answering. One question was, is it only possible to create classification models, or can we do prediction or regression models as well? At this point within the toolkit itself, it's limited to classification models. Regression has come up in a number of instances, and it's something that we're looking at from a roadmap standpoint to automate within the toolkit. For specific projects, we can discuss ways to enable that through the programmatic interface, but for now, it's primarily classification models. Chris, anything you would add to that?
Yeah, that's our focus, classification.
Yeah. Next question was, is there any restriction about the layers that can be used in the TensorFlow model?
Yeah, so that goes back to really the main things you're going to be limited by are the size of the model, the latency of running the model, and then if you go to the TensorFlow Lite Micro, they have more documentation about this inference engine, and they have a link to the ops that are supported in the all ops resolver. So you can see a list of the ops that are supported.
Okay, next question was, does the compute accuracy feature use Renode for quick feather simulation? Is there a way for us to leverage this directly? If so.
So we're not using the quick feather Renode yet for that. It's part of the thing that's on our roadmap, but you can definitely run the library in Renode if you want to.
Next is there a model that you have developed with a high percentage of prediction? Library with Python code.
Can you repeat that question?
The question asked, is there a model you have developed with a high percentage of prediction?
So like a high accuracy with the Python client?
I think that's what's asking. So my thought is the boxing punch classification. If we're talking about an example model with high accuracy that integrates TensorFlow, that would be one that you could look to.
Yeah. Yep. So that's a good example to look at. So.
Then the final question I have listed here was, can we combine machine learning for, say, accelerometer events with handwritten code for other sensors or code that is supposed to run permanently on the S3? So definitely so.
Yeah,
so
definitely.
You had your own business logic or application logic beyond the classifier itself. Think
Yeah.
of this as a library that can be called as a function.
Yeah.
And then on top of that, you could add your own post-processing or any additional application logic that runs in firmware.
Yeah, so if you download the library, it'll give you all the application code, or we have the SDK that is up on GitHub that you can just copy the library over to, but you can write all of your own application logic around that. And the library you can just think of as something you pass sensor data into and get a classification result out of, and then you can add whatever you want around that.
Okay, so if there aren't any other questions, I'll make one plug to say that we have future sessions being planned at this moment. I don't have definitive dates as yet, so stay tuned to our social feed. And by all means, if you have topics of interest, odds are that others have the similar interests. So we welcome that kind of input on our social feeds, discussion boards on Hackster.io for the users that are part of that, but also on the Sensimal Twitter, LinkedIn, and Facebook feeds. Feel free to express any topics that you'd like to see handled in the future. And we'll update that shortly with follow-on topics that we'll have planned for the near future. So thanks a lot, everyone. Appreciate your time, and hopefully you found this very valuable, and we'll look forward to seeing you in a future session. Thanks a lot.
Thank you.